All right, let's dive into something pretty fundamental and often kind of perplexing in the modern tech world. You're building these complex applications, breaking them down into smaller, manageable pieces, microservices. But then you hit that central challenge. How do all these independent services manage their own data but still talk to each other, seamlessly? How do they deliver a consistent experience? It feels a bit like trying to run a marathon where every runner has their own pace, maybe even their own route sometimes, but they all need to cross the finish line together, perfectly in sync. So today we're doing a deep dive into data management in microservices.
That's right. And we're really aiming to cut through some of the noise here. We wanted to show you how these smaller, independent parts of an application can handle their own data needs while still, working together effectively without tripping over each other constantly.
Exactly. Our mission today is basically to unpack the core ideas, the common strategies people use, and crucially, the practical tools, especially in the Java and Spring Boot world, that help you tackle this. We want to give you clear insights, maybe some surprising facts, and really get into the why behind the choices people make. Let's try and get right to the good stuff. So I guess the big question is, how do you keep your data straight when your application's chopped into like 1,000 tiny pieces?
Yeah, that's sort of the Gordian knot of microservices data, isn't it? And it's really where we have to start. So when we talk about microservices, we're talking about those small, independent components of an application. Each one handles a specific, pretty well-defined task. Think user profiles or maybe order processing.
And that independence, that's the cornerstone, yeah.
Right.
The whole point is moving away from those big, monolithic, all-in-one database structures we used to have. But here's where it gets really interesting, I think.
Mm.
Well, each service needs its own data to be truly independent. They have to share or sync up certain information somehow. Otherwise, you don't get a coherent user experience. Like making sure if you update your profile details, that change shows up immediately when you look at your order history.
Precisely. It's this fundamental balancing act. Independence on one side and essential cohesion on the other. And this tension, it throws up, well, typically three big challenges. First, data consistency. How do you make sure all the services have up-to-date, accurate data without creating, a tangled mess?
Right.
Second, independence itself. How do we make sure each service truly manages its own data without becoming tightly coupled, which kind of defeats the whole purpose of microservices?
Yeah, you end up back where you started almost.
Almost. And finally, performance. How do you access and share data across these different services without introducing really painful delays?
Okay, so if each service is supposed to be its own little data kingdom, what's the core principle? How do they interact, given those challenges?
Well, what's truly fascinating here is how a fairly simple principle can bring order to this complexity. The core idea is each microservice should own its data, period. Typically, this means using its own dedicated database. This is pretty much non-negotiable if you want genuine independence and want to avoid that tight coupling.
Okay.
Think about a big e-commerce site, maybe like Amazon. Their inventory service tracks stock, right? The order service manages purchases. The user service handles profiles. Each one has its own data store. Now, they absolutely must coordinate in order has to decrease the inventory count, for example, but they don't directly fiddle with each other's databases.
Ah, okay. So no direct reads or writes across those boundaries.
Generally, no. This ownership model, even though it might sound like more setup initially, is what drives incredible reliability, scalability, and importantly, consistency in the long run.
That makes a lot of sense. Own your own stuff. So with that principle of data ownership nailed down, how do these independent services actually manage to coordinate? How do they share data effectively without just creating a new bottleneck? What are the common strategies we see out there?
Great question. This takes us from the why to the how. We're looking at approaches that balance that independence we need with the coordination that's, well, unavoidable. The first one, and maybe the most intuitive, is simply database per service.
So literally just what it sounds like. Each microservice gets its very own database. Simple as that. But doesn't that just create a different kind of silo? How do you handle something like a query that needs data from, say, 3 different services? Doesn't that get complicated again?
You're hitting on a key point there. Yes, each microservice has its own dedicated database. A payment service, for example, might use its own SQL database for transactions, completely separate from, say, an inventory service using maybe a NoSQL database for stock levels. The pro is definitely that it promotes genuine loose coupling. It lets you pick the right database tech for the job, SQL for payments needing strong transactions, NoSQL for a product catalog needing flexibility.
Okay, that makes sense. Tailor the tool.
Exactly. The con, as you pointed out, is that those cross-service queries get harder. You can't just join tables across databases easily. So you typically need to either aggregate data somehow on the client side, or maybe use one of the other strategies we'll talk about to sync up a necessary subset of data between services.
Okay, got it. Dedicated database for each. What's strategy number 2 then for sharing data without getting tangled up, especially if direct database access is off the table?
Right, that leads us nicely into event-driven data sharing. With this approach, services don't directly query each other's data stores. Instead, when something significant happens, we call it an event, like a order placed or maybe user-updated profile. The service that owns that action publishes this event. It sends it out, typically to a central message broker, like Kafka or RabbitMQ.
Ah, like a central announcement board.
Sort of, yeah.
Yeah.
And then other services that care about that specific event, they subscribe to it, they listen for it. When they hear the event, they react accordingly, usually by updating their own internal data based on the information in the event.
So using your example, when an order is placed, the order service shouts, "Order placed," into this message system, and the inventory service, which is listening, hears it and goes, ah, okay, I need to decrease the stock for that item, is the biggest headache here, just making sure every service actually gets the message and processes it correctly, and only once.
You've absolutely nailed it. That's the challenge. The upside is this approach massively decouples your services. It's fantastic for scalability, and it handles failures much more gracefully. If the inventory service is down for a bit when the order event comes through, the event usually just waits patiently in the queue until the service is back online.
Okay, that's a big win for resilience.
It is. But the complexity, as you identified, lies in things like ensuring reliable event delivery, managing the order of events if that matters, and making sure processing is idempotent, meaning even if a service accidentally receives the same event twice, it only processes the update once. Netflix is a really famous example of using this heavily. They use it to update user profiles and viewing history across many different services, ensuring your recommendations are up to date without those services needing direct access to each other's databases.
That's clever. Great for those big distributed systems where maybe eventual consistency things updating shortly after the event is okay. But what if you need data from another service, like right now, real-time data?
Yeah, for those immediate synchronous needs, we often turn to strategy number 3, API-based data sharing. This is probably the most familiar pattern for many developers. Services simply request data from each other directly using APIs, usually REST endpoints. So for instance, during the checkout process, the order service might make a direct API call to the user service. Hey, give me the current shipping address for this customer ID.
Okay, that sounds way more straightforward to implement, right? APIs are bread and butter for most teams, but it also feels like it could easily sneak those tight dependencies back in, couldn't it? If the user service is down or slow, the order service might get stuck waiting for that address.
That is the exact trade-off, yes. It is simpler in many ways, and it provides immediate strong consistency. You get the data as it is right now. However, it definitely creates synchronous dependencies. The caller waits for the response. This impacts fault tolerance if the user service is down. The order might fail. And it can hurt performance if you have lots of these blocking calls happening all the time. It's generally best used for data that absolutely positively needs to be current at that precise moment.
Gotcha. Okay, so we have database per service, event-driven, and API-based. What's the final strategy? The one that sounded a bit like a time-traveling data logger.
Yes, event sourcing.
Yeah.
This one's a bit different conceptually. Instead of storing just the current state of your data, like the current count balance, services store a complete immutable sequence of every single event that has ever happened to that piece of data. Think of it like a financial ledger. Every change is recorded as a separate time-stamped entry. User created, address updated, item added to cart, deposit made, withdrawal occurred.
Wow, okay, so you don't store the current address, you store the history. Address set to X, address updated to Y.
Exactly. The current state, if you need it, is then reconstructed by replaying these events in order. A banking app is a classic example. Storing every single deposit and withdrawal event makes auditing incredibly robust. You can always trace exactly how a balance came to be. It's super useful for understanding the history and for debugging complex scenarios.
That sounds incredibly powerful, especially for auditing and maybe figuring out tricky bugs. It gives you that perfect historical trail. But I can imagine querying that must be, well, different. You're not just selecting the current state from a table.
You're right, it is different. Querying the raw event log directly can be complex and sometimes slow for certain types of queries. So often with event sourcing, you also build what are called projections or read models. These are essentially pre-aggregated views of the data derived from the event stream, specifically designed to answer common queries efficiently. So you might have the full event log for auditing, but also a separate read model that just stores the current customer address for quick lookups.
Ah, okay, so you sort of build optimized views from the event log, right? So that covers the main strategies, which brings us to the really practical part. With these approaches in mind, how do you actually do this? Especially in the Java and Spring Boot world, what are the tools developers can actually use to implement these strategies without tearing their hair out?
Yeah, exactly. Let's talk tools. This is where the Spring ecosystem, particularly Spring Boot, really shines. It provides a lot of robust, often quite opinionated options that simplify these potentially complex patterns. Let's start with probably the most common one for relational data, Spring Data JPA.
Okay, Spring Data JPA. What's the nutshell version? What does it simplify for us?
In a nutshell, it's the Spring Boot module for working with relational databases. Think MySQL, PostgreSQL, Oracle, etc. It uses the standard Java Persistence API, JPA, under the hood. Its main superpower is how it simplifies database operations through something called repositories. You basically define Java interfaces describing the queries you want, like find by username, and Spring Data magically generates the implementation code for you. It handles a ton of boilerplate. It's absolutely ideal for, say, a user service storing structured profile data in PostgreSQL, where you need strong consistency in AC transactions.
Got it. Less SQL to write, more focus on the business logic. What about when the data isn't so neat and tidy? For those more flexible, less structured needs where JPA might feel a bit too rigid.
Right, for that kind of scenario, you'd likely look at Spring Data MongoDB. As the name suggests, this is the Spring Data module specifically designed for interacting with MongoDB, which is a very popular NoSQL document database. MongoDB is known for its flexible, schemaless approach. So Spring Data MongoDB is perfect for things like a product catalog where attributes might vary wildly, or maybe a recommendation service storing diverse, evolving user preferences. It handles that less structured data really well.
Okay, so JPA for relational, MongoDB for document NoSQL. Now, what about implementing that event-driven approach we talked about, the one with the central message broker? What's the go-to tool in Spring for that?
For building those event-driven systems, the primary tool you'll reach for is Spring Cloud Stream. It's a really powerful framework that dramatically simplifies writing applications that interact with message brokers, like Apache Kafka or RabbitMQ. It essentially abstracts away a lot of the low-level complexity. You define bindings in your configuration, telling Spring Cloud Stream, this method sends messages to this topic, or this method listens for messages on that topic, and it handles the connection, serialization, error handling, and so on. So that order service, sending an order-placed event. With Spring Cloud Stream, it's often just a simple method call configured to publish to a Kafka topic, the inventory service listening, just another annotated method.
Okay, that sounds like it removes a lot of the plumbing work involved in messaging. That's huge. And what about the other end of the spectrum? That synchronous, real-time API-based sharing where services just ask each other for data directly.
Yeah, for making that easier, Spring Data REST is incredibly useful. What this tool does is pretty cool. It can automatically take your Spring Data repositories, the same ones you might be using with JPA or MongoDB, and expose them directly as RESTful web APIs. With minimal configuration, sometimes none at all, it creates endpoints for CRD operations, create, read, update, delete on your data entities. So imagine that product service needing to expose its catalog. With Spring Data REST, the order service could query products without the product service team having to write any explicit REST controller code for those basic operations. It's great for rapid development or simple data sharing needs.
Wow, okay. So it just builds the API for you based on your data model. That's handy. And finally, for that really intricate event sourcing strategy, the one that logs every single change as an event, is there specific Spring tooling for that, or is it more complex?
Event sourcing itself is more of a pattern than something with a single dedicated Spring module. But there are tools that integrate very well with Spring Boot to make it achievable. A key one is Debezium. Debezium isn't strictly a Spring project. It's an open source platform for something called Change Data Capture, or CDC. What Debezium does is it monitors your database's transaction log directly. It reads all the committed changes, inserts, updates, deletes at a very low level. It then captures these changes as structured events and can stream them, often to a message broker like Kafka. Spring Boot applications can then consume these events. So that banking service we talked about, it could use Debezium watching its transaction database. Every deposit, every withdrawal gets captured as an event automatically and published.
This is fantastic for building robust audit logs or for feeding data into event source systems or read models.
So Debezium handles the capturing the change part, and then maybe Spring Cloud Stream helps consume those events.
Exactly.
Yeah.
Often work together beautifully in that kind of architecture. And really, if you connect this back to the bigger picture, all these Spring Data and Spring Cloud tools, they significantly lower the barrier to entry for implementing even these quite sophisticated data management strategies within a Spring Boot environment.
Yeah.
They handle so much of the boilerplate, letting developers focus more on the business logic.
That's a really solid toolkit to get started with. But, you know, in the world of microservices, the solutions rarely stop at just the core framework libraries. There are always other specialized tools and wider architectural things to think about, right? What else should someone listening be aware of as they start building out these distributed systems?
Absolutely, you're spot on. The Spring ecosystem is fantastic, but it often integrates with or relies on other powerful standalone tools. And there are definitely broader considerations. The first big one that comes to mind, especially if you're really leaning into event-driven architectures, is Apache Kafka itself.
Right, the distributed streaming platform. We mentioned Spring Cloud Stream abstracts it, but Kafka is often the engine underneath, yeah.
Exactly. While Spring Cloud Stream provides the nice programming model, Kafka is frequently the high-throughput, fault-tolerant backbone doing the heavy lifting for those event streams. Understanding Kafka's own concepts, like topics, partitions, and consumer groups, becomes important as you scale. A prime example of its use is Spotify. They rely heavily on Kafka to propagate things like playlist updates or playback events across their myriad backend services, ensuring everything stays eventually consistent.
Okay, so Kafka is the foundation. What else?
Then there's Spring Data Redis. We haven't talked much about caching yet, but it's crucial.
Ah, Redis. Right, that's usually for really fast in-memory data storage, like caching, isn't it?
Precisely. Redis is a super fast in-memory key value store, and Spring Data provides excellent integration with it via Spring Data Redis. It's absolutely fantastic for caching frequently accessed data to reduce load on your primary databases. Think caching user session information, results of expensive queries, or even things like rate-limiting counters. For instance, a user service might cache login tokens or maybe parts of user profiles in Redis. An e-commerce site might cache popular product details. This can drastically improve response times for users and reduce strain on your persistent databases. It's often a key tool for performance optimization.
Makes sense. Hit the fast cache first, only go to the slower database if needed. Now, one thing that always seems daunting with microservices, when you have dozens, maybe hundreds of these services potentially talking to each other, sending events, making API calls, how on earth do you figure out what's actually happening when something goes wrong? Debugging must be a nightmare, especially with data flowing asynchronously.
That is a massive challenge, and it's where Spring Cloud Sleuth and Zipkin, or similar distributed tracing systems like Jaeger, become absolutely essential. Spring Cloud Sleuth automatically adds unique trace and span IDs to requests as they travel between your microservices, whether they're synchronous API calls or asynchronous messages. These IDs are then typically collected and visualized by a system like Zipkin. This allows you to see the entire path of a request, which services it touched, how long each step took, including interactions involving data updates or event publications. It's invaluable for debugging latency issues, understanding complex flows, finding performance bottlenecks, or tracking down where data consistency might be failing. Netflix, again, is famous for using these kinds of tools extensively to trace requests across their massive architecture.
Okay, tracing is key for visibility. So we've got the strategies, we've got the core Spring tools, and some important external ones like Kafka, Redis, and tracing systems. Pulling it all together, what are the big picture considerations for our listener when they're actually trying to put all this into practice? What are the tough choices they're going to face day to day?
Yeah, there are several crucial decision points that come up constantly. First, and maybe foremost, is data consistency. You have to consciously decide, can this data tolerate being slightly out of date for a short period? If yes, then eventual consistency, often achieved via event-driven patterns, offers great scalability and fault tolerance. Think product recommendations or maybe social media feeds. But if the data must be absolutely current right now, like checking an account balance before a withdrawal or processing a payment, then you likely need strong consistency, which often points towards synchronous API calls or careful use of distributed transactions, which are complex. It's a fundamental trade-off.
Right, eventual versus strong consistency. What else?
Second, database choice. We touched on this, but it bears repeating. It's not one size fits all. You really need to match the database technology to the specific needs of that microservice. Don't just use PostgreSQL everywhere because you know it. Is the data highly structured and requires transactions? SQL might be great. Is it flexible, document-like, or needs massive horizontal scaling? A NoSQL option like MongoDB or Cassandra might be better. Using the right tool for the job is key here.
And performance, that's always looming large, isn't it? Especially in distributed systems.
Always. So, third, performance. Beyond just choosing the right database, actively think about optimization. As we said, caching frequently accessed data with Redis is often a huge win. Also consider things like read replicas for databases, efficient indexing, and being mindful of chatty communication patterns between services.
Okay, consistency, database choice, performance. What about keeping the data safe?
Good point. Fourth, security. When data is flowing between services, often over a network, you've opened up new potential vulnerabilities. Securing that data access is critical. This involves things like using HTTPS for API calls, proper authentication and authorization between services, maybe using something like OAuth 2 or JWT tokens managed by Spring Security, and ensuring your databases themselves are secured. Don't neglect security in a distributed world.
Definitely.
And finally, monitoring and observability. You absolutely cannot effectively manage a microservices system without knowing what it's doing. This means using tools like Spring Boot Actuator to expose health endpoints and metrics for each service, integrating with monitoring systems like Prometheus and Grafana to track database performance, message queue lengths, API response times, and error rates. And using those distributed tracing tools we mentioned, you need visibility into the health and performance of your data flows.
Wow, okay. Consistency trade-offs, database choices, performance tuning, security, monitoring. It's a lot to juggle. This really raises that crucial question for anyone diving into microservices. With all these different strategies, tools, and considerations, how do you actually choose the right combination for your specific situation? How do you avoid getting paralyzed by all the options?
Yeah, that is the multi-million-dollar question, isn't it? And like most things in architecture, the honest answer is usually, it depends. It really depends on your application's specific requirements. What does it do? It depends on your team's skills and familiarity with different technologies. And it depends on your overall system goals. Are you prioritizing raw speed, absolute consistency, or fault tolerance? But we can definitely provide a sort of guiding framework, some rules of thumb.
Okay, let's try that. Lay it on us. When should someone confidently reach for good old Spring Data JPA?
Spring Data JPA is generally your best bet for services that handle structured data and require strong transactional consistency. Think core business functions like payment processing, order management, user authentication, and profiles. Why choose it? Because it's mature, battle-tested, makes working with relational databases much simpler, and it's ideal when you need those ACD properties. Atomicity, consistency, isolation, durability for your data changes. An e-commerce app using JPA for its order service in MySQL or PostgreSQL is a classic, solid choice.
Okay, standard relational stuff. When does the needle swing towards NoSQL, like Spring Data MongoDB?
You'd lean towards Spring Data MongoDB when your service deals with data that's more flexible, unstructured, or semi-structured. Think product catalogs with varying attributes, user preference tracking, content management systems, activity streams. You choose it because it adapts easily to evolving data models without painful schema migrations, and it typically scales horizontally very well for large volumes of data or high write loads. A recommendation engine storing diverse user interaction data in MongoDB for fast, flexible querying is a great fit.
Makes sense. And for those bigger event-driven systems needing that robust decoupling and scalability.
That's prime territory for Spring Cloud Stream, usually paired with Apache Kafka or maybe RabbitMQ. It's best for implementing asynchronous, event-driven data sharing between services, especially when eventual consistency is acceptable. You choose it because it handles high message throughput, improves fault tolerance, services can fail independently, and allows services to react to changes without being directly coupled. Think about Uber using Kafka ride completion events, trigger updates in payment, notification, and driver rating services asynchronously. That loose coupling is key at their scale.
Right, scale and decoupling drive you towards events. What about the simpler case, that direct synchronous API call for real-time data?
For that, Spring Data REST can be a great starting point, especially for simpler needs. It's best when services need immediate, real-time access to another service's data, and the data model is relatively stable. You choose it because it drastically simplifies creating basic CR-RED APIs over your data repositories, saving development time. A product service exposing a simple REST API for the order service to quickly check current stock levels or product details is a perfect use case. Just be mindful of creating those synchronous dependencies we discussed.
Okay. And finally, if you absolutely need that complete, immutable, auditable history of every single data change?
Then you need to look seriously at Debezium, often integrated with Spring Boot and Kafka. It's the best tool when you're implementing event sourcing patterns or have strict auditing requirements where tracking every data modification is critical. You choose it because it reliably captures database changes directly from the source, the transaction log, ensuring you don't miss anything, and turns them into events. This is ideal for systems needing that comprehensive, unchangeable history, like in finance or other highly regulated domains where proving data lineage is crucial. A banking app logging every single account transaction via Debezium for auditing is a powerful example.
Okay, that's a really helpful breakdown of when to reach for which tool. So summing it all up then, how does someone listening navigate this complex landscape to build resilient, effective microservices? What's the general approach?
I think the key is to start simple and iterate based on needs. For smaller applications or services with clearly structured data, maybe begin with Spring Data JPA. If you need simple synchronous sharing, Spring Data REST can get you going quickly. Then, as your application grows in complexity or scale, scale with events. For larger systems needing decoupling and resilience, lean towards Spring Cloud Stream with Kafka for that asynchronous, event-driven data management. It generally scales better. Always think about how to optimize performance. Don't forget, tools like Redis for caching it can make a massive difference in responsiveness for frequently accessed data in high-traffic services. Critically evaluate your consistency needs. Choose event-driven approaches for eventual consistency when a slight delay is okay, or use APIs carefully for strong consistency when data must be real-time accurate. Match the pattern to the business requirement. And finally, consider your team skills. Leverage the Spring Boot ecosystem because it offers relatively beginner-friendly tools and fantastic documentation.
Play to your team's strengths in Java and the Spring framework to make tackling these complex data challenges more manageable. And remember, you're not alone in this. Leading tech companies like Netflix, Uber, Amazon, they're constantly wrestling with these exact problems and successfully using these very strategies and tools we've discussed to achieve reliable and scalable data management in their massive microservices architectures.
What an incredibly insightful journey through a really complex topic. We've definitely unpacked that intricate balance we talked about right at the start, that constant tension between keeping each microservice independent and capable while ensuring the whole application works together consistently and performs well. It seems really clear that while microservices give you amazing flexibility by letting you break big problems into smaller pieces, the real art, the true mastery, isn't just in the breaking apart. It's in how you intelligently, elegantly, and resiliently put them back together through data. So maybe a final thought for you, the listener, to ponder as you reflect on all this. How might the strategies and tools we've explored today change how you think about building new systems? But maybe more interestingly, how might they influence the way you approach rethinking existing systems, perhaps those older monolithic applications, and consider how they could be carefully untangled using some of these patterns for greater efficiency, scalability, and maybe even unlock new innovation?